It will be here in about 45 minutes. So if you can like stick through the talk, hang in there, don't get too hangry at Camilo, then it'll be here at the end. So yeah, today we have Camilo. He's talking about Git internals. And I will let you guys know who's talking next week at the end of this, because I need to look that up. But yeah, give Camilo a hand.
Cool. So thank you, everybody, for coming. This talk is going to be about Git internals, as you know. I'm Camilo Payan. You can find me on Twitter, either as cpayan. OK, I already forgot how to use a laser pointer. Or CamiloPayan.com, or on the Chadev Slack as Camilo. So this talk is going to be pretty demo heavy. We're going to go back and forth between my terminal and these slides. So the first question is, can everybody read this part? If in the back you can't read it, let me know, because I can always move it up. Yeah? I'll move it up just a little bit, just in case. So, yeah, is it the computer? Let's just keep moving it up. Good? How about now? Cool. All right. So, how many of you use Git every single day? Right, a lot of people. Does everybody know what Git is? I mean, either way, Git is a version control system, the idea being that you can share code, keep a history of your code, make changes to your code, all without losing all your data every single time. If you've ever done the far less adequate, like I'm going to have a folder with each day named, like I used to in college, that sucks. Git is way better. How many of you use something else from day to day? OK, cool. Out of curiosity, what do you use? Oh, what do you use? OK, I don't know it. But neat. So why get into the guts of Git? There are a couple reasons. I mean, you might say curiosity alone. I'm not really into that. Really, I wouldn't really want to get into the guts of Git as long as it's working. But the problem is that it's not always going to work. So when Git goes wrong, it's good to have a mental model. This SKCD comic over here pretty much nails how most people know Git. You memorize a couple commands. You use them like magic words. And if something goes wrong, you just delete everything and re-download everything. That will work for you, but you know, it is not a great way to get through things. Having a good mental model of how Git works behind the scenes, though, will help you either solve the problem yourself or at least know what to Google so that then someone else who already had this problem will solve it for you. So one thing to remember is historically, initially, Git was a toolkit for a versioning system, not a versioning system on its own. So there are two kinds of Git commands. There are Porcelain commands, and there are plumbing commands. These Porcelain commands are the user-friendly commands that are used day to day. So does anybody know any Porcelain commands off the top of your head? Git commit, right. Git add, git fetch, all of these are Porcelain commands. And they're meant for you to use, type into your thing, your CLI, whatever. Plumbing commands, on the other hand, are for the programming to use. It's for the computer to use. So they're not really meant for human consumption. And of course, that's going to be the main crux of this talk, is going to be those plumbing commands. This is all what's happening behind the scenes. So let's get into the demo area. This is a totally clean directory. All we have is dot and dot, dot, dot. You know, those are references to other folders. There's nothing in here. So none of our Git commands are going to work because there's not even a Git repository. That's the error that it gives us. There's no .git repo folder, so nothing Git related works. So our first step to understanding Git is going to be using git init to create a repository. So what it tells us is that it gives us a .git directory. Let's check it out. This is Git in a nutshell as a repository. Everything in here is where Git stores information and everything that drives Git. So there are some parts of this you're probably already used to, or maybe didn't know that you were using, like config. If you set your email or your name, that's going to land in config. If you add a remote server, like GitHub, that's going to land in your config file. Another one that you might have used, how many people use GitHooks regularly? OK, Well, let's take a look at that folder, because that's a cool feature of Git, where you can put in scripts, programs that will run at different points of your Git workflow. If you've never used this before, it's always worthwhile in order to put in linters, stuff that warns you, things like that. Just don't force anybody to use them, because they'll hate you. But today, we're going to be talking about the rest, except for info. We're going to be talking about especially the objects directory, the refs portion, this head file, and also a file that doesn't exist yet called the index. So let's go back. So the first thing first is going to be blobs. Blobs are the building block of Git. This is what your content is going to be considered by Git, and ditto is a blob. So let's go straight into it. I said this is going to be very demo heavy. We're going to go ahead and make a file. Cool. Go ahead and add our ditto into here. We take a look at our file, Pokemon.txt. It's not in our Git repository, of course, yet, because we haven't done anything. Now, how would we create a blob? How do we store this content in Git? What we use is our first plumbing command, hash object. It's going to create the object. So like most of our Git commands, we run Git, the command that we want for it, and we tell it, in this case, to write it to our database. It'll also do it without that and give you the same result. But what's interesting is what we get back from it, which is the hash of our data inside of Pokemon.txt. So this is a SHA-1 hash, and if we take a look at this, what's cool about a hash is that no matter what computer you're on or anything like that, you're going to get the same result back. It's a one-time pad. It takes the content, which I'll explain about this in a second, runs it through the SHA-1 algorithm, and gives you back the exact same output every single time. This is what Git saves. It's got the content of our file, ditto. It's got the type of object that we're creating, the blob, and it has a length of the file and a null byte. Why is it 6 instead of 5? Because of the null character. And just to prove that this comes up with the same thing, we get the same exact hash that we just had. If you want to read those to the end, cool. And what happens here is Git is a content addressable file system on the back end. So that essentially means that it's going to turn out as a key value pair. The key in this case is the hash that we created, and the value is going to be the content of the file. So let's keep looking into our Git repo and see what we got. If you're not familiar with the find command, it's going to list out everything inside of this directory, .git objects, that is a file. And you can see the hash that we just created, that's going to be, well, partially a file name, also a directory name for efficiency reasons, I guess. And how about we take a look at the contents of that? OK, it's gibberish, the file that we just created. But that's because it's a binary representation. This is just catted out. It's a binary representation of the file there. And Git will compress your content in order to store it and give it that key. If we use another plumbing command called cat file, well, we have two different flags we'll try out with this same hash. We'll use -t to figure out what type it is, so that's cool. And we'll use -p to get it pretty printed, which gives us the exact same content that we had before. So in this way, Git will always store that content in a unique way that is set to exactly the content that's inside it. So no matter what you do to your content, if it's slightly different, you're going to get a different hash, you're going to have another object. However, if I kept on running hash object on exactly this, I mean, cool, but it's not going to change anything inside of my directory because they have the exact same key. Let's go ahead and prove that. Let's open up Pokemon.txt and add another Pokemon. That's going to be relevant in a second. And we run hash object and write it to our database again. We have a different hash, different content. And instead of being 6 characters long, it's now like 15 or something like that. If we run cat file on this little guy, we already know that it's going to be a blob. It gives us the whole content. This was actually really surprising to me while I was doing the research on this, because as I understood it, most version control systems will store the changes from one file to the next, but Git doesn't do that. It will always snapshot the whole file and give you a hash based on the whole file. So now we have 2 Git objects in our object database. Both of these are key value stores again. So when you as long as you have the hash, you can get the content that that hash is about, as long as you use cat file, which we just did. Let's create one more to set up the rest. I'm committed to this. And we'll create yet another hash object for it. We get a different hash because it's completely different stuff. And yeah. Now, can anybody tell me like what's missing from this? There seems to be something important to each file that's completely missing from our hash object database currently. Right, the name of the file is missing. There's no way to tell what these files were named based on the hash or on the content inside, because that's not the file name itself. So how do we have file names? How do we tie files together? Because when you make a commit, you can have more than one file in each commit. And yeah, that'll be what we focus on for the next couple seconds. So we do that using trees. A tree will be a data structure that puts together different blobs, puts them together with their names, and can reference other trees as well. That's why they will be trees, because they keep on branching out in that manner. So how do we store a tree? How do we create a tree? Oh, these are good questions. First things first, let's start with our newest plumbing command, in this case, update index. We're going to add something to our new index, and we're going to add our lyrics file. So let's take a look in our Git repo. We've got a new file. It's the index file that I promised you. It's another binary file, and in this case, it happens to do with a particular metaphor that they like in Git, the staging area. So if we run git status, can anybody tell me which command we just walked through very slowly? Add. So we've added this lyrics.txt file to our staging area, and that would be the Porcelain equivalent of the 5 steps we just did. So this is what's happening when you write git add. On the other hand, here's a challenge. We can still add files that don't exist anymore as long as they exist in our object database. So what do I mean by that? We had a file that just said ditto, right? But our current file says ditto and pseudowudo. So how do we add that file that says ditto? That way we keep the history that we created where we added the new Pokemon at the end. Well, we can still use update index, and we'll add it. But in this case, instead of sending it a file name, we'll use the cache info flag, which tells it this information is in your object database, but it is not currently in the file system. So just look at the object database and give it a file permission. These kind of look like the permission codes that go with the Unix file system, 644, 755. If you've ever run WordPress, you've had to deal with that at some point. But Git doesn't actually respect all of the same permissions that Unix does. So this is one of the 3. There's another one for symbolic links and another one for 755, if I remember correctly. And what we need now is the hash for that very first, right, this one, that very first object that we created, the first blob. And in this case, we're going to give it the file name that was left out of the information before. We take a look at git status. We've added Pokemon.txt, and we know that it's not the latest version because it still thinks there are changes between what we have in staging versus what we have in our file system. Now, we can go ahead and create our tree object at this point using the plumbing command write tree. So let's take a look at this object. Everything is run off of the same concept of a hash key and a value. We'll cat file, take a look at the type. It's a tree. Pre-print the contents, and we'll take a look at what our tree looks like. It's a list. We have our permissions, the types of the things that the objects that we put inside our tree, the hashes for each one of them, and the file names that go with it. And this is looking a lot like the kind of thing that we would put in a commit. Trees kind of pull double duty as well, where they also represent directories in your repository. So let's make Dragon's repository directory, and let's create a file inside there so we can play with it. At this point, if you're not crazed by hunger, you might be saying, hey, you skipped a couple steps. But update index will do more than one thing. And in this case, it's creating the object, the blob object for our Pokemon.txt file inside Dragons, as well as putting it inside of our index file. We take a look at that. It's in our staging area now. Let's write the tree again. So we got a different hash from what we had before. Let's take a look at what is now inside of this tree. We have the same two blobs that we were looking at, as well as another one, which is a reference to a tree that's just called Dragons. In this case, if we took a look at that tree, what are we expecting to see in it? Yep, another one of those. And if we take a look at that blob, it's Dragonite. So what's left to finish off creating a commit? Just have to commit it at this point. Right now, what we have are tree objects that are sitting in our objects database, but we haven't actually created any commits yet. And we can prove that by taking a look at git log. There are no commits. So we'll give it a not very meaningful commit message. And we'll use the plumbing command commit tree. This is the hash for the tree that we want to commit. And that gives us yet another key that we can plug into cat file. It's a commit. It keeps track of all of these things by using a pretty simple set of rules, just blobs, trees, and commits. And this is what a commit looks like to Git. It keeps track of the tree hash that we created. It gets some information out of your author, out of your config, the author and committer. It keeps track of the time that the commit was made. And it gives you your commit message. So cool. Now we have changes still sitting around. And you can see this by using the plumbing command, we didn't actually do anything to our index. So what we can do now is create our second commit. And the easiest way to do that, since we do want to use the file as it is in the file system with ditto and sudo is add that file directly. If we take a look at status, now there are no changes yet to be committed. You run git write tree. And let's create our second commit. Cool, we've created yet another commit. Let's take a look at it. It has a different time, different timestamps, a different tree, and a different message. All these things are things that we would expect to be different. And let's go ahead and get the history based on that commit. Oh. Extra space. I only have one commit. I made 2 commits, but I only have 1 in this case. That's because the commits don't immediately know each other, and when you use the plumbing commands, they won't know about each other at all. So you have to connect each commit to the next commit as you create them, or as Git creates them while you're doing all that work. So this was how we created this commit, but we want to relate it back to the previous commit that we had made. One thing that's interesting to note is in my notes, I get to use the exact same SHA-1 for everything because the contents were the same and all of that. So I could kind of see them by sight. I can't do that in this section. Can anybody tell me why? The times. The commits are going to be different. I can't use the same, it won't have the same content this morning as it does now. So we want the commit tree to be the same, but now we want to tell it that there's a parent using -p and the hash for the previous commit. Now when we take a look at this new commit, which you can see the hashes are different. This started with a 30, this starts with F6. We have a little extra information. We have the same tree hash that we were looking at, but now it has a reference to the parent hash, and it can go ahead and look that up in the object database very quickly and easily. So if we run git log against, oh, okay. We've created a commit history. So that's it, right? There's still one more thing. If we run git log like we would normally, I'm on the master branch, nothing. None of this is still referenced with our master branch. So we have our commit objects. We have pretty much everything we need, the content, everything. But we still need to put together our references to each commit. Well, not necessarily each commit, as we'll see. The way that references work is they are going to be files inside of your Git repository, inside of the refs folder in particular, here on the bottom, that point to particular commits and give them a human readable name that we like to call branches. The other important reference to note is here, the head file, and we'll take a look at that right now. What is in your head file? It's a reference to a reference. So this is going to reference whatever is in refs head master. So let's take a look at our refs head. There's nothing in there. Master is kind of a canonical name, but even if there's nothing in there, we'll see in a second that it won't actually work. Oh, where's my cursor? Here we go. Let's get our commit hash. That's going to be useful. We know that this commit hash works. It gives us exactly what we want. It has our history. So we'll take that commit hash and put it directly into refs heads, and we'll give it a name like test. If we run git log test, it gives us that commit. If we take a look at git test, gives us the hash, pretty much what we would expect. And on top of that, without actually having called branch, I can now check out test, and that works. It considers it a branch. Everything is fine. Let's check out master. Well, that doesn't work. We didn't have a master in the first place. We don't have a master now. But since everybody's going to be mad at us if we keep things this way, let's use the safer git plumbing command, update ref. With the same hash. And now everything kind of works as we expect. Because of some other things, it can tell that this is the reference to both of these. Let's take a look at what happens with head during all this. No, that's not going to work. Sorry, let me get to the right place. Right. So this is pointing to master like we had it before. If we check out our new branch, which was really just a file in the refs folder, that gives us a reference to the test reference. And if we decided to, has anybody ever gotten into a detached head state? That's what happens here. You are checking out directly a commit, and if that commit doesn't correspond to any of the references in your refs folder, it takes a look at the head, notes that it's just a straight commit, and now I'm in a detached head state. So what happens to our head file in this case? Instead of having the clean refs heads master, it just shows you the commit message. So it's not the end of the world. Everything still pretty much works. And if you check out a branch, you'll get back to what you had before. So that's what's happening at that point. And now that you kind of know the idea, it's kind of easy. I haven't actually verified how all of these work, but it's kind of easy to conceptualize how other more complicated Porcelain commands also work. If you're cherry picking a commit, you want to grab a commit from one branch and put it on the end of your other branch. So what happens in that case? You're taking that same commit, you're using the tree hash that it has, you change the parent, and that gives you a new commit, a new hash. And then you change the parent to whatever's on the ends, whatever's the current head of your target branch. Rebase seems like it would be something similar. You figure out where they diverge, and you have your list of commits thanks to the chain of commit parents, and then create new commits based on that, based on the chain of parents, but with the same tree hashes, because those tree hashes are going to be saved in your object database for all time. And if you see the objects database now, it's huge. Let me do the find again. We've got a bunch of objects in here. All of those, some of these we aren't even using, like trees that we left behind, objects that we didn't care about, blobs that we didn't care about. Commit, that second commit that we created that didn't have the history is still here. That's why, so Git will hold on to everything for you. You can run git prune and get rid of objects, but generally it's just going to keep on holding on to every single object that you have. And that is pretty much it. As far as acknowledgements go, Pro-Git is a great book. The last chapter that I never got to before I started doing this talk is all about Git internals and has a lot of, like this talk is very much based on that. And there's also a very good talk and workshop by a woman named Emily Gier, I guess, called Dissecting Git's Guts. And there's also a really good workshop at OSCON where she has like a workbook that you can work through. If you want, I can post that in the ChaDev Slack. And yeah, so definitely hit me up in the ChaDev Slack and send me any feedback if you have any. Thanks for your time, and thanks. Huh? Yeah, I don't know much more than what I told you, but.
One of the most common requests is trying to like restore a branch you've totally messed up. You want to go back to some commit that you've lost because you've modified history and all that. I assume, do you know offhand how to crawl through all those commit objects and find like the commits, like filter it down and all that kind of stuff? Are those plumbing commands?
There's a command called filter branch and some others that you can run through all the objects in your database.
This would be a commit that's been orphaned.
So
it's not part of a branch anymore.
I don't know if there is a porcelain command or even a plumbing command to do that, but you could use the plumbing commands to do it. You could run through each file, each blob, and figure out the contents from that, or in this case, you want the commits, not the blobs. But you could look through the commit messages using a pipeline, I guess, in Unix. That sounds reasonable to me. I don't know. That too. So Git has a ref log for every change you make, and for that we're going to need a more complicated repo. So I'm going back to work. Because Git doesn't just keep a list of all the commits that you made, it also keeps a list of all the changes to your branches and commits that you made. That way you can go back in history. So these are rebases. I could undo a rebase in spite of the fact that I already did it by going back instead of to a particular commit to a particular point in time. So had 15 heads ago, so on and so forth. That's a really good one to remember. Huh? You want to pass them the...
So after looking at the internals of Git, and like a lot of it seems very conceptually simple, do you feel tempted to write your own version control system now?
No, not even a little bit. That just sounds like a nightmare, actually.
Almost embarrassing to ask, but I noticed at the beginning you used the E flag for the echo command, and I wasn't sure what that does.
You know, I wasn't sure either, and I'm still not. So what happens was, I did it without the E flag, and I did it with, and it worked one time, it didn't work the other time. And this man page isn't really giving me much, so maybe it didn't matter. Oh, it has its own? And now I'm pretty sure that I made up my story because it seems to be working now. So, you know, I don't know.
Well, everyone give Camilo a hand. So food should be here shortly, within like the next 5 or so minutes. If you guys want to hang out for that, because we got food for everyone. Also, next week, Jay Baker is talking on something, but we're not sure yet. Do you know yet?
Yeah. Yeah, I'm going to do, it's very ops heavy talk. I'm going to do immutable deployment with Ansible, Packer, and Terraform. Just a real simple demo, just to show you how easy it is.
Well,